Alright, hey guys, welcome back to Intelligence Maxing, day 36. So it's been a while, but here I am. Hopefully, we'll learn something today. We'll find out in the next 30 minutes to an hour. But today, I kind of want to go over the idea of convolutional neural networks. There's this book that I ended up getting for one of my classes, and this book talks about, it's called Deep Learning, which I guess is the standard textbook nowadays for a deep learning class. I don't know. But there's a chapter on convolutional neural networks, and this is something we're learning about in class. Honestly, I'm a bit behind, so I don't really fully understand what this is. I'm hoping I can kind of spend some time today going over and trying to figure out what the hell convolutional neural networks are. So with that being said, let's get started. Okay, I'm gonna pull up this and have my Anki flashcards open. All right, let's do it then. I might be silent for a little bit just because I'm reading through some stuff in the book. I think if I find anything interesting, I'll just summarize it. So there's about 11 sections here. First one talks about the convolutional operation. So let's just go in order then. Convolutional networks, also known as convolutional neural networks, or CNNs, that has a known grid-like topology. So it seems like the big idea is that convolutional networks are simply neural networks that use convolution in place of general matrix multiplication in at least one of their layers. And whenever I think of maybe a classic neural network, you have the idea of W transpose X, where W transpose is just a vector or a matrix of weights. And then X could be a vector or a matrix of inputs. And then that kind of matrix or matrix vector matrix multiplication results in some type of activation, linear activation. Now, I guess what the difference between convolutional neural network is that instead of using that basic W transpose X, you have this convolutional or convolution operation that replaces it. I don't know what a convolution is. I remember hearing about it in class, wasn't really paying attention, so I think we're about to find out what this is. This chapter, we first describe what convolution is. Next, we describe the motivation behind using convolution in a neural network. Okay, I'm gonna come back. I realized that I don't have a pencil with me, and I want to take some notes in the margins here. And also I might need to write some stuff down too, so I'll be back in a sec. Okay, made it back. Got my iPad too. And a pencil. Need to find a place to plug this in. So there's this one thing where he talks about topology. What is topology? Study of geometric properties and spatial relations unaffected by the continuous change of shapes. It sounds complex. And there are continuous deformations, infinitesimal conditions associated with the varying solution P of a problem this. Maybe ChatGPT has another way of what is topology? Not theory manifolds. So when they say continuous function, I guess it's in this picture, these are all connected somehow and never ended. So when they say that data has a grid-like topology, what is grid topology? I guess topology is a study of, it refers to kind of how it's structured. How is time series data grid-like? Is it just because you're going one by one by one by one? I'm not too sure, but I think what I'll do is move on to the section on the convolution operation. Okay. T minus A. Okay, so it seems like the idea of a convolution is to apply some weighting function or maybe some weight to measurement, and the idea is that if you take the average or maybe the weighted average of recent measurements, then that might eliminate some noise in previous measurements. I think that's what the basic idea is. Okay, so they throw some vocab at us. The convolution, so the x is referred to the inputs. The second argument, in this example, the function w as the kernel. The output sometimes is referred to as the feature map. Sin is not realistic. Usually when we work with data on a computer time will be discretized and our sensor will provide data at regular intervals. For example, it might be more realistic to assume that our laser provides a measurement once per second. The time index t can take on only integer values. If we assume that x and w are defined only on integer t, we can define the discrete convolution sum. So what is A again? A is equal to age of measurement. So the position at the age of measurement and times the weight of t minus the age of measurement. I'm kind of confused on why they do t minus a. So in the machine learning applications, so t minus a can be thought of as time index t. So elapsed time maybe? T minus a is equal to elapsed. Machine learning applications, the input is usually a multi-dimensional array of data. So it could be a 2D array and the array. And the kernel is usually a multi-dimensional array of parameters that are adapted by the learning algorithm. So again, what is the kernel? The kernel is the weight function, okay. We refer to these multi-dimensional arrays as tensors because each element of the input in kernel must be explicitly stored separately. We usually assume that these functions are zero everywhere, but in a finite set of points for which we store the values. Yeah, there's some complex math thing that I don't fully understand what they're talking about, so I'm going to skip over it for now. Well, we can implement the infinite summation as a summation over a finite number of array elements. Convolution over more than one axis at a time. If we use a two-dimensional image I as our output, we probably also want to use a two-dimensional kernel K. I guess we're M and N. Okay, so they talk about kernel flipping. I'm not entirely sure what exactly it means. Mathematically, it just seems like they switch the sign of I minus M. 2D convolution. Okay. So the cross correlation, you have kernel, which is M and N. I think that gives you probably the weights, and I plus M. I don't know what I and J represent in this, so maybe they'll talk about this a little bit more. Okay. Okay, so they do have an okay. I plus M. Okay, so they do have a picture which makes this a bit more clear, but it seems like the idea is that the kernel, which is the idea of a weight, is applied to a specific dimension of the input, and then you have this element by element multiplication here. Sparse interactions, parameter sharing, and equivariant representations. So there's also another terminology here called receptive field. I think this has to do with in a neural network, what are the actual what are the units that or neurons that affects the output neuron? So sparse connectivity, that's one of the big ideas behind convolutional neural networks. I think the idea is that instead of having all of your neurons affecting all the, okay, let me reword this. Instead of having a single neuron affecting all of the output neurons, or all the neurons in the next layer, you're kind of limiting the effect of a single neuron to the next layer. And you do that with the kernel, because the kernel itself can limit the dimension of your output. So usually the, what's it called? Traditional matrix vector multiplication, it'll I think the final output will give you the activations that are sent to every single neuron in the next layer. But with the kernel, that limits the dimensionality of the output. So it might send the activation to maybe 2 or 1 out of the 3 total neurons in the next layer. I think that's the big idea. So let's see. Receptive field. Oh, Puggy, come here. Puggy, come here. No. I'm trying to get my dog to hop on. All right, let me see. Okay. Field 4. Parameter sharing. Okay. Okay, so I think so. One thing they talk about here is the idea of parameter sharing. It seems like when you use a kernel, the parameters of the kernel doesn't or the values of the kernel don't change. Okay, so the values of the kernel don't change, and the parameter itself, what's it called? So the parameters stay the same, and that's what the idea of parameter sharing is, I think. So this transformation can be described by a convolutional kernel containing two elements required. Okay, so this section talks about convolution versus matrix vector multiplication, although it's a bit confusing. Of course, most of the entries of the matrix would be 0. We store only 9. Okay, this one is a bit confusing. I still don't understand why they multiply by 3. 2 multiplications and 1 addition per output pixel. Yeah, not too sure. Okay. Okay, so equivariants still have a bit of trouble. So I'm just going to move on to pooling. So there seems to be 3 different stages in a convolutional layer. KY invariance. Try to have 1 pixel between pooling regions. So this is nonlinearity outputs. Pooling region of 3 pixels. Okay. This invariance and equivariance stuff is kind of complicated. And how it ties into pooling. From what I'm understanding so far, the idea of equivariance and the idea of invariance is that the, I guess, final outcome should not be affected by slight changes in the input. And so when we're talking about inputs, usually in these convolutional neural networks, they're pictures. And so let's say you transform some pixel within this picture, maybe shifting over the pixels over to the right by 1 unit, or rotating the pixels, rotating the image thereby. I think you have to apply linear transformation to rotate the pixels. Then you get this idea of invariance in which the final output should be the same. Hey, Bogey. So is this a stride of 2? What is downsampling? Okay, so I do have to go run right now with your boy Teddy, but I think I made some okay progress. This is pretty hard. It's a lot of stuff. I have to do a lot of thinking. But I think to recap, we just kind of went over the basic idea of what a convolution is. It seems to me it's like this weighted average of this operation that kind of computes the weighted average of some type of input. And in the context of these convolutional neural networks, we refer to a function that gives we refer to an image as an input and then the weight function as the kernel, and then that will give us a feature mapping, which is the output or the actual convolution computation. So the main idea behind why people do this, it's an alternative to the traditional W transpose X, where you're multiplying a matrix of weights and a matrix of inputs. In this case, the parameters themselves is not a matrix of, it's still similar to a matrix of weights, but the actual dimensionality of that weight matrix is a lot smaller compared to the traditional W transpose X, where where the weight vector should have I think the weight matrix, that number of columns and number of rows. So the number of rows should match the number of inputs and I think the number of columns should match the number of output kernels, output units. So that's something I have to review. That's something I probably need to review before I kind of dive in a little bit deeper. So I'll come back to that, and I'll see you guys in the next one. Peace.